welcome everybody, and I guess a belated Merry Christmas. I think we all have. I recognize some of the faces around here. Some of you I don't know, but anyway, I'm Roger Hammond, KC0MWM, and this is the guy that I've been sharing all this balloon stuff with, another Roger, and this is Roger Franzen, KE08KT. That doesn't roll off the tongue.
No, not as good. Yeah.
Anyway, there's a little spot in here where we typically do a little, well, this is the second time we've done this, but where we are set up to do kind of a little background, what our education is, what our work things have been. I'll just tell you real quick, I've been at the power plant in Grand Island now for a little over 30 years. Spent most of my time in either instrumentation or computers and networking and controls. It was always kind of a natural progression to get into amateur radio and some of the hobbies associated with amateur radio. And as some of you know and have even been a part of, I've done some latex balloon flights, the bigger ones, and of course tonight we're going to talk about much smaller. So I'll let Raj tell you a little bit about himself, and then we'll turn the lights out, let you get a nap, and we'll run some slides and talk about it.
Yeah, I hope you guys didn't have too much to eat. I worked in the power industry most of my career as well. I started out as an operator and an instrument technician, and then I ended up going back to school to get an engineering degree, and Roger actually took my place at the power plant, and that's how I ended up meeting him at first. We hit it off immediately and have been good friends ever since. And a couple years ago, Roger, and I'd helped him out with some of his latex balloon projects, and he approached me and he said, hey, I got this new project I'm going to be working on, and it has to do with these little balloons and radio trackers and all kinds of stuff, and wondered if I'd be interested in helping him out. And it's like, well, I said I'd be disappointed if you wouldn't have asked. And so we dug into it, and it's been a pretty interesting run. And hopefully you guys will think it's interesting as well.
Yeah.
So
we'll go to that end of the room so that we can read some of the notes on our slides. We'll try to talk loud enough. If anybody has a problem hearing us, let us know. We'll try and speak up a little bit. The microphones are for Brad's benefit and the video. So.
No, they're for Phil's, the president. So.
Ah, you didn't tell me it was the Prez. That's
Yeah.
all right. Well, we'll try and get rolling here. All right, just a little bit of humor. The whole R-squared engineering thing. When Roger went on to college to get his engineering degree, and I took his spot at the power plant, well, he came back to work in the summers and at Christmas time, so we started working together quite a bit. He was kind of showing me the ropes out there, and we were kind of joined at the hip quite a bit, and we sort of became R-squared at the power plant. So it was only sort of the natural progression to be the R-squared engineering. So
we milk the whole double Roger thing a lot.
Absolutely. All right. So like we said, used to do some of the latex balloon flights. These balloons are obviously much bigger. They start off, 6 to 8 feet on the ground, and by the time they pop up at 100,000 feet, they're anywhere from 24 to 26 feet in diameter. So the balloons we'll be talking about tonight are much smaller, and then you can see Raj down in the corner being
being a paperweight, essentially.
And of course, with the big latex balloon flights, you can fly things as heavy as a GoPro camera and various other things to get cool pictures like this. And this was probably one of my favorites, I think, from the last flight that we did. I won't take a lot of time here, but this is looking from the south. Let's see. This is southwest of Lincoln. So if you look, first of all, right there, that little furry stripe there is a jet contrail looking down at 30,000 feet, because this balloon is actually up around 90,000 feet. And somewhere over there, that's Lincoln. And if it was a little clearer, you can actually see the 12,000-foot runway of the airport. So Omaha's kind of obscured by the clouds off in the distance, but this balloon was, well, it ended up over by Beatrice. This was one that I think
Is that the one you launched from the Edgerton?
Yeah, we flew your payload of the Raspberry Pi and.
Oh, I was on that trip.
Yeah.
Yeah.
Well, yeah, because your wife had to come and get us. Yeah. Anyway, a little bit of history. I won't spend a lot of time on this, but this whole amateur radio high altitude ballooning. This is the guy that started it all. Bill Brown, WB8ELK. Bill launched his first flight back in 1987, and to date, he's still doing all kinds of flights. He's done 600 plus. He has designed and built his own Pico Tracker. And Bill does a lot of outreach to like high schools, middle schools, grade schools. He's a real cool guy. That NASA hat is for real. He does work for NASA. He's an electrical engineer. He's retirement age, but I think he loves what he does, and he's still working for him. So this past November, he posted on. I guess there's some perks for working for NASA, right? When you're helping on the Artemis project, he got a chance to get his picture taken with the astronauts and promptly posted it on his Facebook page. All right, so why Pico balloons? Well, number one, it's a whole lot cheaper. The latex balloons nowadays, the balloon sizes that we were using were about, they're over $100 now. Helium has become the unobtainium. Unless you're a medical institute or, something with a big contract, helium is just, well, they won't even sell it to you. I tried to buy from the guy that I used to buy from back when we were doing the latex balloons, and he said, he goes, I won't even tell you what it costs because I can't sell it to you anyway. So we ended up going with hydrogen, which of course is a lot cheaper, and it has some benefits as long as you're careful with it. Batteries, I could easily do 20 or 30 bucks worth of disposable lithium batteries for all the payloads when we were doing this. Of course, there's the price of gasoline, and this last flight ended up with a blown radiator when we stopped to get the payload. My radiator cap didn't bother to vent, but it found another place to vent the pressure, and well, we ended up getting a ride from Roger's wife. She had to come and get us from Grand Island, so that was fun and expensive. All right, so the difference between the two types of balloons. The latex balloons, it's typical latex. They're real stretchy. They're made to expand as they climb in altitude. These meteorological balloons are specifically designed to shred into little pieces when they get to altitude, and usually they do a pretty good job of that. There's been some cases where we've brought down some pretty big chunks of latex that can foul the parachute, and that's all behind us. So now, what is a Pico balloon? Well, I didn't come up with the name. The guys that started doing this before we did decided that, well, these are smaller balloons, so let's call them Pico balloons, and maybe someday we'll have nano balloons. I don't know. But the typical balloons that are used right now are the ones on the left are the 32-inch Yokohama. You can buy them without any coloring, no foil, silver mirroring or anything. And then I just bought a batch of the ones on the right because they're back in stock and you don't have to buy so many. And you can also buy them here in the States. But they're 32-inch round party balloons. It's nothing special. It's just like a regular party balloon without the writing on it. And let's see, what else can I tell you about that? Ah, yes, the super pressure. I guess I should read my notes.
Is that $13 for one?
It is. You know, when you're comparing that to the $110 for a latex, it's like this is significantly cheaper and more affordable to play around with. So they call these super pressure balloons because they will stretch a little bit, but not like latex. So what happens is we put in a small amount of lifting gas, in our case hydrogen, and we put just enough in so that when this thing gets to a specific altitude, it's completely inflated because the pressure has equalized or very close to what it is outside. And at that point, or right before then, it becomes what they call a superpressure balloon. So it's a little bit, if you think about this balloon floating at altitude, it's a little bit like a submarine being under the water at a specific depth. We're just kind of doing the opposite, you know, instead of water, we're talking about air.
And what we shoot for is for it to be buoyant and get to a particular altitude and then stay right around that altitude. Slightly affected by barometric pressure and temperature, but for the most part, it hangs out where it's supposed to be. We've got a spreadsheet that somebody made up that if you put in all the correct parameters, it tells you how much hydrogen you need to put in to get to a specific altitude. And we found it to be pretty accurate.
Yeah.
If we use a little scale and measure how much lift the balloon has, and they've leveled off right where we expected them to.
So what is a Pico Tracker? Well, it's nothing more than a little tiny amateur radio transmitter. It's got a little microcontroller to control everything that's going on the board. It'll have some sort of a location device like GNSS or GPS receiver chip. And then, of course, you have the transmitter. In our case, and in most of the cases of the guys that have built these, you're looking at about 10 milliwatt output. So not very much, and I'll get into the benefits and the not so benefits of having that kind of power in just a little bit. Of course, all this needs to be solar powered because batteries aren't going to last very long if you're trying to make it around the Earth, and it takes, you know, days on end to make that happen. Ideally, it needs to be lightweight because these balloons, the more weight that you put on them, the lower that buoyancy altitude will be. So the sweet spot is less than a half an ounce. So if you can do anything less than half an ounce, you typically will get more altitude out of it. And well, I'll show you here in just a bit about, yeah, there we are. So the one on the left was our first design, and that is pretty much everything except the string that you use to tie it to the balloon that we also check the weight with. So 14 grams is about half an ounce, and that one was a little bit heavy. And I just did the empty soda can in the middle to give you an idea of what kind of weight we're talking about. Now the one on the right was our latest design, and it looks like it's heavier, but some of that's those cardboard tubes that the 20-meter antenna is wound up on. So if you subtract the cardboard tube weight, that one's down to about 13 grams. So that one's a little bit more where we wanted it. All right, there are a handful of hams that have built and designed their own trackers, and they sell them online. So if you're interested in getting a party balloon and some gas to put in it and want to launch one yourself, you don't have to go through what we did. You can just go out and buy one. I'm going to say price-wise, I think they're anywhere from about $25 for the cheapest one, maybe $40 for the cheapest, and up to about $150 for one of the most expensive I've seen. So why did we decide to build our own? Well, who doesn't like a challenge, right? This was the first challenge we had. If any of you have ever played around with electronics. I'm guessing that most of it was probably of the through-hole variety, where, you know, resistors and diodes and those things have actual leads on them that you can see and poke through the holes and get some solder on. All that stuff's too heavy for a Pico Tracker, so we had to learn to deal with all the surface mount stuff. And I've got a few little gadgets here. I'm going to
Might be better to pass those around afterwards, you think?
yeah, we may do that once we get the lights on. I've
Yeah.
got some breakout boards and some of our old trackers that we'll send around. So good call, Raj. Thanks for keeping me in line. And how small? Well, really small, like tweezers and microscope small. That pencil on the left is pointing at some of the little capacitors in that strip there. And those aren't even the smallest ones that are available, but that's as small as we went because it was getting difficult to work with. We ended up buying a reasonably inexpensive digital microscope so that you could use a video screen and place the components. I don't think I've got a slide for it, but if any of you have ever done surface mount work, the way we did it was when you order your circuit board, you can order a stencil that is cut out where all the pads are for all those components. And you tape it in place, and then you use solder paste instead of a soldering iron and solder. You smear the paste on, peel the stencil off, and then the paste is on all the pads where all the components are going to go. And then we start placing those components on the paste, and that's what Raj is doing there in that picture. And then once you have all the components in place, then you run it through what's called a reflow oven. Well, that's how the big guys do it. We kind of made a little DIY reflow oven out of a toaster oven and a controller. And it basically runs it through about a 5 or 6 minute cycle. It heats up the board, it starts to melt the paste, and then it goes through what they call reflow, and that's when the solder actually melts and the components kind of find their own little positions on the pads. And actually things can be somewhat crooked and they'll right themselves most of the time.
And one of the challenges of doing that too is that when you pick up one of these tiny little parts with a pair of tweezers and then you like squeeze the tweezers a little bit too hard and the part goes shooting off, and I mean, they're gone, okay? You'll never ever find it again unless it was something that we thought was really important we had to look for. But it turns out a lot of these surface mount components are cheap. You can buy 100 resistors for $1.
Yeah.
And and it turns out that, to me, I always thought there was a barrier to trying to design things with this, and it turns out that it's really not as bad as you think it would be. And between the software tools and the little oven and the stencils and stuff like that, we were able to make some pretty good quality boards without, well, you know, a huge amount of effort. So it's definitely doable if you want to try it out.
What's the software you use?
We use a program called KeyCAD for circuit board layout. It's open source. It's really, really good.
Yeah, we complain about some of the options that it doesn't have from time to time, but then you have to remember what you're paying for it.
One of the things that really impressed me about this entire project was the access to technology. And when I graduated from college, a circuit board layout program like that would have probably cost $5,000 to $10,000. And now you get on the internet and download it, and it's free. And it's highly capable, and like I said, it works pretty well.
Yeah, it's amazing what you can do with, you know, a computer and some time. So I'll back up a little bit about the through-hole components. If any of you have ever done any hobbyist work where you're breadboarding electronics, it's relatively easy with the through-hole components because you push them into the breadboard, you add some jumpers, you connect things up, and it works. Well, when the cool chips that you want to use are surface mount, or if you are required to use surface mount components, you don't have that luxury. But many manufacturers and a lot of the hobbyist electronic places make these little things called breakout boards. Not all of them make exactly what you want, but in this case, we couldn't find somebody that used this little clock chip on a breakout board of the type that we wanted. So the very first circuit board that we created was a breakout board to be able to try and make the transmitter that we wanted to make. And this little chip is really, between the chip and the crystal, that's basically the transmitter for the device. There's a whole lot of configuration and a whole lot of programming that goes into the microprocessor to make it do what you want, but in a nutshell, there's your transmitter.
This chip is programmable. It's basically a clock synthesizer, and it's got a crystal hooked up to it, and you can synthesize any frequency from 2,500 hertz up to about probably 150, 180 megahertz, something like that.
Yeah.
With probably percentage or decimal point accuracy of output. And then there's a couple different ways you can modulate the frequency. The particular model we started using has an analog input on it, and you could modulate it with a voltage and essentially kind of like pulling a crystal or pulling the frequency. Or you can also, if you don't need to change the frequency too quickly from a modulation standpoint, you can actually program it or write to it digitally and have the frequency change. And we've done both of those depending upon which vintage or model that we were using. So
I'm going to let Raj continue down this path because he was the one that ultimately got this to work. We decided with the first tracker that we were going to use APRS because there's an APRS infrastructure all over the world. And, you know, all you need is line of sight with that transmitter, and I'll talk about that later. But that's all you need. When you're out over the ocean, you don't have that luxury. But anyway, we decided to go with APRS. And so for that, we needed that, you know, around 144.39 megahertz here in the States. And then it also needed to be frequency agile, but I'll let Raj talk about that little bit of a journey to get to that point.
So if you guys are familiar, the APRS uses audio frequency shift keying, and so we basically modulate the carrier wave with an audio signal, and the audio signal jumps from one frequency to the other, which gives you either a mark or space. And there's a lot of different ways you can do this. Some of the guys were using pulse width modulation and filtering it, and the CPU that we had actually had an actual pretty high speed D to A converter on it. So we decided to just send an audio signal into it. We had a hard time getting, there's some de-emphasis or some emphasis on there depending upon what frequencies you use, and we kind of had a hard time getting the continuity of the signals straightened up the way they needed to be. But ultimately, we were able to program using some arrays and different things in the CPU. We were able to send this audio frequency out and basically feed a bit stream into the CPU, and it would correspond by putting out the different audio frequencies and get the modulation, and it worked.
It did.
Yeah.
And it was kind of cool the first time that we transmitted a call sign and had a little Kenwood handheld that was for APRS, picked it right up, and it was like, hey, we might actually be able to do this.
And if I can say too, everything that we did on this project was a challenge. You know, from learning to do the circuit boards, and it turns out that RF design is really complicated, and there were a lot of things we had to learn about that. You know, the impedance of traces and constant impedance transmission lines, and you know, every chip had its own idiosyncrasies and things that had to be done to it and stuff. And So it was just a continual number of challenges. One thing, the microprocessor chip we used, the data sheet for that's over 1,000 pages. And in order to program these things and increment it into a design, you really need to, have a pretty good idea of what's going on and hardware in and stuff. And so there was a huge amount of research that we had to do with practically everything we touched. Then, and we didn't mention it, but we're using the Arduino programming environment, and which is also an open source free thing that's very powerful and easy to use. It programs in the C language. And fortunately, there's a lot of guys who've done things like this. If you look around a little bit, you can usually always find somebody else who's already got some software written. And we reused and re-engineered a lot of software, and there's no way that we could have done it from scratch. But
we talked about it initially, and then it was like, this is going to be
that's not going to happen.
No.
And even when you've got somebody else's program, in order to implement it and maybe make changes to it, you have to understand the program enough to be able to get into it and do that. And so we still put a lot of effort into, analyzing somebody else's software and figuring out how it worked enough to where we could get to the point and modify it and make it do what we needed to. So yeah, it was a continual challenge.
So one of the things we talked about was that worldwide APRS infrastructure. Well, that's very true, and it's pretty cool over the US because we have the same frequency throughout the entire continent, right? Well, not so in the other places. So depending on what location you're flying over, you need to be able to change frequencies. So we had to come up with a way to make this frequency agile so that it would change its own frequency based on where it was at. And we talked a lot about that and ultimately landed on this little algorithm that someone had come up with called a point and polygon. And it doesn't matter what shape the polygon is, how big it is, how small it is, if the math that's done on this, if you're inside the polygon, it's a 0. If you're outside, it's a 1. So we were able to create polygons for the different areas that we were going to be flying over. And we sort of cheated because if you're, as long as you stay above the equator, you don't have to deal with as many frequencies. The likelihood of a balloon traveling from the northern to the southern hemisphere is unlikely, but it has happened, and there's actually been some guys that it's gone from the northern to the southern, stayed there for several months, and then made its way back to the northern hemisphere. So if ours would have went to the southern hemisphere, it wouldn't have been on the right frequency because it wouldn't have even known about it. Anyway, so we made some small polygons in Grand Island, and there was a couple afternoons Raj and I were traveling around with the GPS and the program changes and watching to see if the LED changed when it was supposed to, because, okay, now we're outside of that area or we're inside that area. There was some programming errors, but we got through it, and evidently it works because...
And again, it was surprisingly accurate. We'd be driving along and say, okay, when we get past the street, we should be switching into a different point, and it would do it.
And again, the free tools and the technology available to you, it's like, this is Google Earth that doesn't cost you a dime if you have internet access. So I was able to create polygons, and from just drawing points around the different areas, and then you just make either the KMZ or the KML file, and you could get all of the latitude and longitude of each of those points, and then put that into the formula in the program to be able to tell it where it's at. Now, you'll see that one red area there. I guess I should mention that there are a few places over the Earth that you are not supposed to transmit APRS from the air. And that is the United Kingdom, for whatever reason, They don't allow aerial APRS. The country of Yemen, and of course our good friend Kim Jong-un, so North Korea. So you're not supposed to transmit over those areas, and of course we wanted to make sure that no transmit part of it worked well, because we didn't want to be the reason that we started World War III by any means. But anyway, this is, I think, that's a chunk of one of the first schematics. So this drawing program that Raj was talking about that's free to use, it's called KeyCAD. It's a great program. It has large libraries of components. You basically draw the schematic, and then you can run some checks on it to make sure that you have all the points defined, make sure that you have symbols correct and pinouts, and then from that point you say, okay, I want to make a circuit board. And when you go to the PCB editor, it takes all of these components and it just clumps them all together in one spot. And well, that's great, but it doesn't have any auto routing for your traces, which in our case wasn't terrible because it wasn't super complicated, but could you imagine a motherboard or something like that?
So have you guys used this software? Has anybody done any PC design software with it? Okay, I was just curious. Yeah, like Rod was talking about, and what's really interesting about this, if you draw the schematic correctly, when you port that over to the circuit board, you assign footprints to what all the components are going to look like, and it gives you this big glob of stuff called a rat's nest. And then you start moving these footprints around and place them where you think you want them, and everywhere there's supposed to be an electrical connection between a copper trace, there's a line between those two. And so if you do the schematic correctly, your circuit board will be routed without error because you have to have every single one of those things hooked up. And so it's an amazing tool, and he's talking about more sophisticated programs like this will actually do most of the routing for you automatically. And it turns out that the computers aren't really smart about doing that, and they kind of have a hard time doing it, and that's what makes the programs expensive. And so we had to route this all by ourselves, but none of the boards we did were that complicated where it wasn't a huge challenge.
Right. And one of the things that we've constantly marveled at, not only do you get to see, where all the little copper traces and the pads and everything are for your components, but once you're done with the circuit board layout, you can open up the 3D viewer and it gives you a little picture of what your board is going to look like when you have it made. And that's just, I don't know, I think it's super cool.
Have you talked about JLC? Is that going to come up here at all yet? Or? Well, and I guess we can talk about it a little bit.
Go ahead.
These particular boards, these are 4-layer boards. And so you've got a top and bottom copper traces, and then there's also 2 more layers that are embedded in between. And that really simplifies the layout process because you can assign one of the internal layers to power and the other one to ground. And so instead of having to route power all over these places, you just run a via in there and it's essentially automatically hooked up. And so, and you can kind of see where the CPU's out there. The red is the top layer and the green is the bottom layer. And we don't actually have the copper pores in between shown on there. But this company that manufactures our circuit boards, and there's a lot of them out there now, but they're based in China. And a board that's 100 centimeters by 100 centimeters square with 2 or 4 layer is $2 a piece. No, it's $2 for 5 of them.
Oh yeah, $2 for 5.
Yeah, $2 for 5 of them. It's incredibly inexpensive for the quality of a board that you can get. These will do traces down to, I think our traces on here were maybe 12 to 15 mils, and they've actually got the capability of going a little smaller than that, but we wanted to be conservative, make sure everything was going to work. But and then as you can see that we started out to do troubleshooting and stuff. We've got some additional things on the board there, but once you fly, you're never going to need a USB connector again. And so you can see this board segmented right here, and after we had it all programmed and knew that everything was going to run, like on the day that we were going to launch, we just break that part off, and that way we can shed the weight on it, and but still have the capability for doing troubleshooting and programming and stuff before we get ready to launch.
So they'll let you buy 5, or do you have to buy more?
Five's the minimum quantity. Yeah.
Yeah. If you only want one, you're going to get 5.
But you're talking about,
Well,
from
at least you don't have to buy 100.
Right.
no,
Right.
yeah, and that's another thing too. It used to be that you would have to do that. You'd have to buy large quantities, and now that it's very affordable. It costs probably $15 to get them shipped, and it takes a couple weeks to get them, but the quality is really good, and there's a lot of options for
Yeah.
Where do you get the power? You take the power.
Yeah,
You get to the power?
we'll get to the power. Yeah.
So this was version 1. We had decided kind of early on that, I see that little red board there, that's not ours. SparkFun out of Colorado sells those, and that's like the little Arduino, a smaller version of an Arduino that you can buy on a board that size so that you can do your own little projects. And we thought, for starters, it was hard because this was at the tail end of the bulk of the pandemic, and chip shortages were everywhere, and we were having a hard time getting the processors that we wanted. In fact, so much though that even after we decided to go away from this version, that we ended up buying boards like this from a Chinese company for less money than we could actually buy the chips. Now I know they weren't they
were
weren't
counterfeit.
Yeah, they were counterfeit chips, but we had good luck with them. And I'm not an advocate of doing business with China, but gosh darn it, they make it hard not to at times when you get good quality boards like this, and they don't cost that much if you're willing to wait. Anyway, with this board, what we decided to do was to put the processor and the power supply and everything on, let SparkFun take care of that. That's the little red board, or the company we bought those from. And then make our own. And so off to the left, upper left, you'll see that's the supercapacitor. That's the battery in our system. The little white chip is the GPS receiver. This thing, that's another one of those chips that's got I don't know how many 100-page document, and has all kinds of features, some that we used and some that we didn't. The other little item off to the right, the 2 items off to the right of that, the little square guy, that's a temperature measuring chip. And then we also had an atmospheric pressure sensor that we never got to work quite right. It was a bit frustrating, and it was kind of heavy anyway. So in later revisions, we ended up doing away with it. Let's see what else we got. So we got the
that's a power supply. So we used a buck boost switching regulator that puts out 3.3 volts. And since it's a buck boost, it can deliver that power anywhere from about 2 volts up to 5.5 volts, and still give you a regulated output. And so that's the actual integrated circuit chip for that. And then this is an inductor. Most switching power supplies use an inductor, and it's funny how it's much bigger than the chip is. But that's
one of the biggest components we have.
This is a radio chip, or the frequency synthesizer chip, and then we've got a multi-pole low-pass filter, the actual RF outputs on that pad. This is a crystal for the radio, and then we had a few other glue components and things related to. We wanted to make sure we could wake the chip up, or wake the board up when the power supply voltages, or what we call the battery voltage, were within particular limits, with some hysteresis and things. And so the rest of the stuff is basically support for that.
So yeah, Doug had talked about, or had asked about power. Well, like I said, we can't use batteries, so we end up using solar cells. And we use the solar cells to charge the supercapacitor, and then the supercapacitor ends up being our battery or our storage media. And that, of course, works really well as long as the sun lights out. Now, the advantage that we have flying at the altitude that we do is that there won't be any clouds. And if there are, well, it's probably going to bring the balloon down anyway. We'll get into some of that, I think, here in a little bit. The amount of lift that these balloons have just to get where they need to be, it's like if they take on any moisture at all, I mean, like we're talking even like a teaspoon of water, it's going to be enough to start making the balloon descend. So higher is better, especially in the summertime, because some of those thunderstorms, as we all know, get, you know, crazy high with some of those peaks and could knock something like this out of the sky.
And when we launched, too, to his point, it needed to be a relatively cloudless day, because just if the balloon is passing through clouds and you got a little bit of dew on it, that would be enough to change the weight dynamics to where it couldn't get up above that, or it would actually bring it back down.
So version 1, we thought of everything. Let's go fly one. Oh, wait. we started testing. Oops, we forgot this. Oops, we forgot that. And Raj is a retired electrical engineer, so he had a little bit more time to mess with this. And mess with this he did. You can go ahead and tell them about your experience.
We had several things. We wanted to measure the voltage of the batteries and be able to transmit that voltage back, or voltage of supercap. Turns out we forgot to put the divider resistors on. And so that was kind of important. And then, you know, you find out that you missed a particular connection, and so you got to have jumpers in there. And then we'll get to this in a little bit, but we placed a couple components. They're called load switches that allow you to turn or to switch power on and off. And we would selectively power components down to save energy. For instance, we wouldn't turn the radio on until we were getting ready to transmit, and as soon as we got done transmitting, we'd shut it back off again. And we had a little issue with that radio too that I'll get to in a little bit. But so it's pretty common that, particularly on your first design, when you make something like this, that you're going to forget something or do something wrong. One of the other things we did is, I don't know if you guys are familiar with the I2C communication, but it's like a two-wire communication that's pretty common for integrated circuits and things. And we ended up getting them backwards. And it was just a mistake on the schematic, and so the board got routed exactly the way the schematic showed, and we couldn't get it to work. And so once we found out that they were backwards, then I'm there with a magnifying glass and X-Acto knife trying to cut 15 thousandths thick traces and get them scraped off. And it turns out this is number 30 wire wrap wire here, and you can see that it's easily as big or larger than traces on the board, and even the, you know, the pins on the chips and stuff. And so it was pretty, you know, it was time consuming and painstaking, but we were actually able to get a working model out of that with all of our little modifications.
And then?
Okay, and this is something, and we'll bring this up, if you guys are designing things like that, all the manufacturers will put out data sheets, right? I think everybody's familiar with them. And typically towards the back of the data sheet, there will be some information or application information on how to lay the board out, what to do with pins, bypassing power supply, bypassing capacitors and stuff like that. My advice would be to pay attention to that, okay? Because what we did is this particular chip has, I think, 4 or 5 different clock outputs, and they have separate power supply inputs to them so that you could essentially power components with different voltage ranges, different supply voltage ranges. And since they consumed power, even though they were idle and we only needed one output, we left the remaining outputs unconnected. And it turns out that we started running this board and we were having terrible problems. It would lock up and we couldn't figure out what was going on. And to make a long story short, there was some weird lockup condition that happened inside the chip because the power pins that were going to the outputs had nothing to do with the actual operation of the thing itself, but the outputs, and they would make the communication interface latch up. And once it latched up, the only way you could get it back was to power it down and start it back up again. And so to prove that, I took this tiny little, this is probably like number 35, 36 wire.
38, I
38
believe.
gauge magnet wire, and got a magnifying glass out and cut traces and soldered up and got some power distribution to power up those pins that we'd left unpowered. And as soon as we did that, it started working just fine. And so always pay attention to the manufacturer's recommendations for board layout. And you know, if they tell you that a pin needs to be tied high or something like that,
Tie it high.
Yeah, you need to make sure and do it. Yeah, and again, you can see this is the number 30 wire wrap wire there, and you can see how much bigger it is than the other things.
It looks huge by comparison, and it's.
Oh yeah, and I took a soldering iron tip and put it in a metal lathe and drilled the center of it out and then stuck like a resistor lead, and that was my soldering tip that I used to be able to solder those little pins.
But necessity is the mother of invention.
Yeah.
And because he had such fun trying to troubleshoot those tiny components, for the next version, Raj goes, you know, we really need to bring some of those points out to a test header so we can actually put a scope probe on them or get a meter lead on them. And it's like, yeah.
Yeah, because you can't even get a scope probe. There's no way that you can just get an individual lead there to try to see what's going on. And so if you don't have a spot that you can hook onto, you can't tell what's going on.
So this was the second version, and we incorporated everything that we knew was wrong, and problem solved, right? So we built up a couple of boards, and I got a call from Raj one night. He goes, hey, do you have any issues getting a GPS fix? And I went, well, now my lab or my shop is down in my basement, so getting a GPS fix, you know, subterranean is kind of difficult, especially with these small receivers. But Raj has had great luck. He's on the main floor. He's next to a window. You know, he's never had any problems. And it seemed like it was taking an inordinate amount of time, even if he could get a fix. And anyway, we started. Now, you'll notice that there's some extra circuit board up around that little white rectangle is the GPS antenna. And I'm going to back up here just a bit, but you can see where that was the original, right? He's just sticking out there all by himself. But I thought, well, it'd be nice to have a little more meat to be able to tie on the string and stuff. It's like, yeah, I'll leave some copper away from it, but let's just go with this. This'll work.
And you're worried about the antenna getting bumped and getting broken off or something, and so it's like neither one of us know anything about RF design, so it's like, yeah, we'll just slap that antenna in there. There's some open spaces around it that there's no copper or no power planes, and it'll be fine.
Well, the Johansson company that makes these antennas, right in the data sheet, it says, hey, if you need help laying out an antenna, you know, let us know.
So I talked to this guy on the phone, and he goes, yeah, send me your design, and I'll take a look at it. And within 24 hours, he comes back and says this.
Hello, Roger. This is not going to work. This antenna must be on the edge of the... Anyway, you can read it. So it was... it was time to make some changes again.
And so it turns out, and you guys probably know more about antennas than I do, but just the presence of those thin little 1.6 millimeter copper planes that were adjacent to that antenna was enough to just totally kill the antenna gain. And typically when we'd power one of these boards up, the earlier versions in my office, I'd get a GPS lock in 30 seconds or less. And sometimes this thing went for 10 or 15 minutes. And then every once in a while we would get a lock. And so it's like, you can't fly like that because it's never going to work.
And I don't remember if I had pictures of the... Nah, I don't think so. We ended up, we each took an option, and we tried to crudely mount that antenna away from the board to see who could come up with the best, you know, just to see if we could make it work. And Raj took a tiny piece of coax and extended that little rectangle out past the edge of the board. And I took like just a little single wire. Anyway, we did some comparisons with, again, the free software from the GPS company, and we were able to determine, you know, which one was going to be better and all that. But the bottom line was we needed to get rid of that extra copper around the outside.
As soon as we extended the antenna out past the edge of the board, then we got our signal strength back, and you can actually read the GPS chip, and it'll tell you what your input signal strength is, and that was what was keeping it from working.
Yep. And let's see, we talked a little bit about where we got the boards at. Great company. If any of you are into 3D printing, you know that can be fun. If you'd like to have some 3D prints, but you don't want to buy a printer, these guys do 3D printing. They also do resin printing. Well, I should say they do both filament and resin printing. My grandkids have gotten into playing Dungeons and Dragons with their parents, and they wanted some little characters, and I was going to try to print them with a filament printer, and the resolution was just, the parts were too small and my nozzle was too big. I bought a couple of their pieces, a couple of their designs from this same company, and I think it was like $3 for the pieces and the shipping, if you were willing to wait a couple of weeks. So they got their little characters that they designed for a little bit of nothing. I'm not advocating shopping at China, but gosh, if you want cheap, good, or inexpensive, good quality boards, and that's the name of the game when you're in the hobby world, right? And this is, so far we have nothing but good things to say about this company. So we finally got our third design. You can see I ended up printing some little trays to put the components in, because if these things have markings, you can't see them without a magnifying glass, you know, or a microscope. So we would take the bill of material list that the program will spit out for you, brought that into a spreadsheet and added component cubicle numbers to it so that we knew the quantity of the components that were going to be used, and we put them in the little tray, because typically Raj and I, he would assemble one, I would assemble one, and then we would stick them in the oven and bake them. It's like we always did it in twos. That way we both had one to play with and run experiments on. And yeah, let's see what's next. So once you've got a board ready to fly, then it's time to prep the balloon. Now, you wouldn't think you'd have to do anything except put some gas in it and let it go, but that's not the case. There's a global community of these Pico ballooners, and I'm a member of one of their email lists, or a member, I shouldn't say a member, but I subscribe to one of their email lists. And these guys have been doing this for, the better part of 10 years now. And they've figured out all the tricks. And I heed a lot of their advice. And one of the things that they say to do is to pressurize these balloons, to leak check them, and also to stretch them. Now, you wouldn't think that Mylar would stretch that much, but it does, and it will. And if you don't do it on the ground, it's going to do it in the air, and that you're going to sacrifice altitude because of it. So we got the magic number from our good friend Bill Brown, the guy that the NASA engineer that's still doing this. He seems to have a lot of really good advice and a lot of the answers that seem to work well for him and others. So it was like, hey Bill, how much pressure do you put on these balloons? He said, well, we usually take ours to like 0.35 psi. That doesn't sound like a lot, but that balloon is pretty tight. Mm-hmm. You could play it like a drum when it has that much pressure in it. And we would typically leave it like that overnight at a constant temperature, let it stretch out, and then the next day we pull a vacuum on it to suck all the air out of it, because we're going to administer hydrogen, and we don't want a mixture of air and hydrogen of any kind. So then, like Raj had mentioned earlier, we use a gram scale. And what we are trying to do, I'm not sure if I have, no. I thought maybe I had a slide to show you that. We'll take like a calibration weight of about 50 grams. We'll put it on the scale and zero it out. So now, because we've compressed that load cell a little bit on the scale, now we can pull up on the scale to get a measurement. And we'll put enough hydrogen in it so that it will, it'll lift the payload, and then an additional 6.5 grams of what they call free lift. So, for instance, that one tracker picture we showed was like 13.1 grams. We'll try to get the free, or the total lift, the 13.1 plus 6.5, and that's the number we're looking for. So, we'll gas it up, try to keep that free lift within like a half a gram, and then seal it up, and that's where we stay.
So on the ground, you can see here this balloon is inflated with the proper amount of hydrogen in it. And on the ground it's going to be, pretty small and compressed. When it gets up to altitude, it's going to look like this.
And so, on one of the coldest days in December, we went out early in the morning to let this thing go. A couple of our friends came out to join us and take some pictures and see the spectacle. And the one guy, when we pulled that balloon out of the garbage bag, he goes, "That's it?" It's like, I know it doesn't look like much, but that's what'll get us there. Well, so the first flight, you can see the track. It left the center of Nebraska, and throughout the day it made it to the East Coast, and then by that point the sun was starting to go down, so of course it went to sleep for the night, and we never heard from it again.
And we have no idea what happened, It could have gone down, had a component failure, who knows.
So it's time for flight, that came later, I think. Flight number 2. Not really any changes. We kind of went through the same motions. Changed call signs. Raj and I kind of alternate our call signs on these trackers. That one, I think we had, 15 minutes after we launched it, we stopped hearing from it. And we got one more packet towards the end of the day that put it clear out here in, I think, is that Minnesota? Yeah, Minnesota. Never heard from it again. So we started thinking, what are we doing wrong? It seems to work when it's close to home. Well, we decided that maybe it was a power thing. You have to look, this is December, so low sun angles. You're talking about short days. So you're not, and this thing has to have pretty good sunlight in order to charge the capacitor enough to bring everything up and actually start doing its thing. So we said, maybe we need to change our solar panel array. And so we decided to try something that we had heard one of the, and no jokes here, but one of the Polish guys who has done a lot of this decided to put one of those small neodymium magnets on the face of his tracker board, and it basically turned it into a compass so that it was always facing the right direction, like south or north, depending on how you have the magnet on there. So it was time to do some experiments. If you look at the end right there and at the other end, those are little cylindrical neodymium magnets. And we took a cheaper party balloon, put just enough gas in it to float it in my garage to see if we could make it stay facing the same direction all the time. And it did pretty darn good. Enough that we decided, okay, it's a little extra weight. You know, we won't get quite the altitude that we've been used to, but let's try it.
Because I think those magnets weighed half a gram a piece or a gram a piece.
Yeah, it was.
And you know, you wouldn't think it would be that much. And the idea was it wasn't going to be rigidly pointing towards the north, for instance, or the back of that would have been pointing towards the north, so the solar cells are facing south. And we angled them a little bit as well too, because the first ones, they were pointing straight up. And so we thought, well, if we can get it pointed towards the sun and be a little more straight on, we get more energy out of them. But so it didn't necessarily point there all the time, but it would have always had some kind of a restoring force there that most of the time it was going to be pointing towards the south. Obviously, if you had stronger magnets in there, you could have made it just whip right around. But the whole thing with this design is weight was everything. And so you had to think in terms of every component. You know, we were adding up the weight of it and stuff because, you know, everything is significant.
By the way, the 2 coils of wire, like on each end of that tracker, that's the 2-meter antenna for the APRS coiled up, and those are
Guitar strings.
Guitar strings. It's like I believe it's the G string, if I'm not mistaken. Insert your own pun. Let's see. We've got. So this was the 3rd flight, and as luck would have it, we were able to make it all the way around. Now, this was very spotty coverage because of APRS and because of line of sight. You have to remember, as we all know, that the Earth is round, and the curvature of the Earth, you know, the higher up you are, the longer the distance you can see. But even when you're up at around 40,000 feet where these things live, it's still only about, as I recall, 7,500 miles, something like that. And this is a 10 milliwatt transmitter, so if there's anything more powerful on the ground at the same time it transmits, this loses. So we discovered that worldwide infrastructure we were counting on was kind of hit and miss. And I can show you on the next slide. Those were the days that we received some sort of report. It was enough that we could tell that we had it up in the air 6 months. We actually lost it for, what was that, about a month. We thought it had been down. And then one of our friends who was kind of following the flights, he goes, hey, he goes, I think I saw number 3. He goes, well, this is an old link, so maybe that's, I said, well, what's the date on it? And he goes, well, it's like September. And I went, holy crap, it's still up there. Well, anyway, we know that we got 5 laps out of it, and you can see the various places where it checked in. One of the things that tells us is that our point and polygon frequency changing algorithm actually worked. One of the things we learned by moving on to the next step here is that we may have benefited from a temperature compensated crystal oscillator. This one didn't have that, and the next version that we ended up doing did, and it's incredible how much that helps, obviously. But yeah, so we managed to make a few trips around the planet, and now it was like, you know, wouldn't it be cool if you could just see its activity every day? And the guys that are doing this and having incredibly good luck with that are using whisper technology. Has anybody done whisper on the digital modes? Okay, then you know what I'm talking about.
Got a few whisperers.
Yeah. First of all, I didn't have a clue, all right? I've done some digital stuff. Whisper was like, I don't even know what this is, but let's look into it. So Raj and I started looking for, you know, any kind of papers on it, any information. It's like, what? Well, we found one, you found one really good one, and he was actually able to make some sense of the technology behind it. I just kind of nod my head and go, yeah, that's cool, you know? Let's build one.
Yeah, there's a lot of stuff going on under the hood of the Whisper protocol. that this guy designed into it for data integrity and stuff like that. It's amazing what he thought up. I was able to follow it from I guess a technical standpoint. It's like, okay, I see what he's doing here, but I never could have thought of it myself and never written a program for it. But it was pretty interesting to see what he did.
So I don't think I have many slides of that, but so we started a full redesign. We were going to go with 20-meter whisper, and actually it was easier to come up with a workable whisper signal than it was the APRS.
Right.
We found some code that somebody had shared online, threw it into one of those clock oscillator chips with the right crystal, and lo and behold, it looked like it was putting something out. Well, I don't have a whisper receiver, so I guess we're going to have to build one. So strung up a 20-meter dipole. I decided to use one of those little cheap $35 SDR, those software-defined radios, the little USB sticks. Got the software from, what is it, WSTX or whatever his name is. Anyway, long story short, we threw this together at my house, fired up the little clock oscillator chip, and lo and behold, there's the call sign.
It worked.
So we went to work designing yet another board. Let's see. We decided to shed the pressure sensor because we had enough problems with that, and it was heavy anyway. We decided that we would do temperature, monitor voltage, and now, as you guys that know the whisper protocol, you know that they don't have any way to do, well, first of all, latitude and longitude. It just does grid squares, right? And we can't do altitude because there's no altitude slot. We can't do, well, somebody a lot smarter than us came up with a few ways to be able to do that. So as you know, it's a 2-minute transmission that does what? Your call sign, the grid, a 4-digit grid square, and the power level that you're transmitting at, right?
It's about 80 bits it transmits in 2 minutes.
Okay.
Yeah.
Well, these guys devised a way to take, okay, so let's do call sign, 4-digit grid square. We'll use, instead of transmitting the power level, we'll convert the altitude to a power level so that we can know what altitude it's at, a rudimentary altitude, like I think it's like a couple thousand kilometers or 1,000 kilometers. I forget how we did it,
Yeah,
but
it'd be 1,000 meters.
and then immediately following that first 2-minute transmission, you transmit another one, but not with your call sign. It's a created call sign that doesn't exist anywhere on the world. So there's like 3 different prefixes that you can use that aren't used anywhere in the world, and that's Q, and I'm going to forget the other, 0, and I think 1. So we ended up going with Q. So our second call sign transmit, or our second telemetry transmission, has a Q, and then the third digit is a number that we choose to try to be different than other ballooners. So it was Q, a space, a 5, and then 3 more characters. The second digit ends up being the number of GPS satellites in use and the temperature. The 1, 2, 3. The fourth and the fifth digit end up being, now let's see, I'm getting myself confused. The fourth digit is the voltage that gets turned into a letter so that you know between like, I think it was like 3 volts and 6 volts, and they divide that up into 26 slots. And then the next two digits are the 5th and 6th grid square characters, so you get a little bit more resolution on your location. And then the power level in that transmission ends up being the altitude less than 1,000 feet. So it gives you another number to put together so you can get a more defined altitude. Now, trying to remember all this and look at those call signs and go, oh yeah, I know right where it's at, right? Again, somebody a lot smarter than us came up with, actually our friend Bill Brown came up with a Python programming script that looks for your call sign on the WSPR database, and then if he knows when to look for that telemetry call sign, it goes out and pulls that as well, and then it takes all that information and unencrypts it and then makes an APRS string out of it, and it pushes it to the APRS website, which is why you can see our WSPR balloons on the APRS website with latitudes and longitudes and altitudes and voltages. So pretty creative use of a handful of characters on something like that. But we were nothing short of amazed. So the first time that we got one of these functioning after we got the new boards, we were kind of just running some reality checks here before launching it, and it was just sitting in my backyard on a step ladder with some wire, you know, tied to my shed in my garage.
Yeah,
and
you can't really see it, but the wire is going from there to there.
And there you have it. We were getting coast-to-coast receptions from 10 milliwatts on 20 meters. Just crazy. I'm still amazed. Even
Yeah, the signal level that's actually being picked up by the receiving antenna has just got to be phenomenally small.
so we have flight number 4 was the first WSPR flight. We went out and we had a leak in the balloon apparently. We launched it. It was doing well. It got up to around 30-some thousand feet, and then it started coming back down. And it's probably laying on the ground somewhere around Creston, Iowa. It didn't make it very far. So we weren't beat. It's like, let's do this again. This time we'll do a little better job of trying to check for leaks and assure that we've got a nice solid envelope. We launched number 5 on August 27th, I believe. And as far as I know, we haven't heard from him for a few days, but I think it's still up there, and number 6 is reported in today. And they both look just like that, except without the cardboard tubes. We wind up that 36 gauge magnet wire onto cardboard tubes to make it easier to deploy once we get out to the place we're going to launch it. Because that stuff is, well, if you've ever been around tiny wire, you know it's like hair, and it's pretty easy to tangle, and it's a big pain. But
Hard to see in the grass. And so you can see we got rid of our magnets. We didn't need those anymore. We changed the angle of the solar cells so that even as if this thing's rotating around, that at least 50% of the time, one of them should be pointed towards the sun. And then of course we've got how long are these antennas?
20 meters.
Yeah.
No, actually
right.
10 meters. I'm
Yeah.
sorry. It's about 30 feet. Yeah.
Right. And so one of it just hangs down, the lower level, the actual active one hangs down just below. And then we tie the other half of the dipole, which would be the grounded side, on the string. We put an extra long string on between the balloon and that. And so it supports the antenna on the top side. And then, you know, it's pretty delicate too. And we can't launch these if it's very windy, because the balloon, once the thing's in the air, it's essentially moving along with the current. And so we've actually clocked these over 200 miles an hour. Typically in the jet stream, they're running 70, 80 miles an hour most of the time. So it takes, you know, 10 days to 2 weeks to go around the Earth. But just depending upon where they're at and what the weather conditions are, sometimes they can go much faster, much slower. But it's literally at the behest of the wind. Once we let go of it, it just goes wherever it's going to go.
So,
So they've been in, both of these 4 and 5, I think 5's gone maybe 10 times around, 10 or 11 times around, and 6 has probably done maybe six or seven
yeah.
circumnavigations that we know of.
We had a little bit of trouble earlier in the winter. They like to go north for some reason, and they would get into the Arctic Circle, and there was no sunlight. So it's like we would have to rely on the technology that's available to us. There is, and I don't have a slide on it, but your weather guy will know about this, but the high split models, you can use a tool that's available on NOAA's website to, I believe it was initially designed to track like nuclear fallout particles in the upper atmosphere or dispersion of mists or bad things. Well, we can use it for these balloons. If you know a current location, you can get like a 10-day forecast of about where it should be, and it's awful darn accurate. It's like if you put in accurate information as far as the altitude and the location, it's pretty darn accurate. And what we were finding is that they would go north into the Arctic Circle, and it's like, okay, the high split model says we should be able to be back in the sunlight in about 6 days, so you get on that 5th, 6 days, and you're like watching for it to show up, and sure enough, usually within a day or so, it would end up back in the sunlight where we thought it would be.
But we had a couple times we got contacts from like Australia with this balloon being up in the northern hemisphere on a 10 milliwatt radio. It's just quite amazing.
Is that just one transmit a day?
Every 10 minutes.
10 minutes. Yep.
Yep.
Yeah. As long as the sun's shining, as soon as it's got enough power to wake up, then it starts transmitting.
So the four
And-
minute transmit.
Right. Yep.
No
So
problem with the power, or is it a little, it's,
depends on what the sunlight energy is, right? There's been a lot of times where we'll get the first transmission and we won't get the second one. And so we think that, we got the super cap charged up, and then as the radio is transmitting, it's drawing that down, and it may even get started on the second transmission, but it runs out of power before it gets there, and then it shuts down and resets and wakes up again. And so it's continuously cycling through there. But yeah, so, and it's just, we're talking, well, we transmit it, the baud rate's 1.6 baud, and I know you guys are, used to, you think about what Ethernet is these days and stuff, and it's just exceptionally slow, but it's very robust. So anyway, that's the thing. If you guys got any questions, we'd be happy to try to answer anything we can.
We've got some toys
show
we
and
can
tell.
pass around if you're interested in seeing some of the actual, instead of just pictures.